Welcome to part 24 of Matrix and Determinant English series. In this part, we will solve one question concerning the most frequently asked applications of matrix and determinant. Let's dive into the question. For what value of k does this system of equation have a unique solution, no solution, and infinitely many solutions? Before proceeding to solve the question, we have to rearrange the three equations in such a way that the expression containing k comes to these two positions, meaning if we consider the variables and the constant terms as a column and the equations as a row, the expressions containing k have to be in the third and fourth column of third row. It's customary to write linear equations in the form x is first followed by y and z, but it is not a general rule. We can write z first, then y and x, or y first, then z and x. Because such rearrangements don't change the final result. To make the writing suitable for our reshuffling, let's swap x and z. That's in the first equation, minus 4z comes to the first place, minus 5y, plus k squared minus 6 times x comes to the third place, equal to k. Similarly, the second equation becomes 2z plus 3y plus x equal to 1, and the third equation becomes 4z plus 8y minus 4x equal to 4. Still, the expressions containing k don't come to the final row and column. If we exchange first and third equations, we can bring the expressions containing k to the positions where we need, meaning equation 3 becomes equation 1, that's 4z plus 8y minus 4x equal to 4. Equation 2 will remain as it is, 2z plus 3y plus x equal to 1, and equation 1 becomes equation 3, minus 4z minus 5y plus k squared minus 6 times x equal to k. Now, we bring the expressions containing k to the positions where we need. To solve this equation, let's form an augmented matrix consisting the coefficients of z, y, x, and constant terms. In the first equation, the coefficient of z is 4, the coefficient of y is 8, the coefficient of x is negative 4, and the constant term is also 4. In the second equation, the coefficient of z is 2, the coefficient of y is 3, the coefficient of x is 1, and the constant term is 1. In the third equation, the coefficient of z is negative 4, the coefficient of y is negative 5, the coefficient of x is k squared minus 6, and the constant term is k. Our next operation is to convert these three elements to 0 and these main diagonal elements to 1. To change this 4 to 1, we have to multiply row 1 by the reciprocal of 4, that's 1 over 4. To change this 2 to 0, we can multiply it by negative 2 and add it with this 4. So the formula that can change this 2 to 0 is negative 2 times row 2 plus row 1. To change this negative 4 to 0, we can add it with positive 4, which is already here. So the formula that can convert this negative 4 to 0 is row 3 plus row 1. Multiplying row 1 elements by 1 over 4 gives us 1, 2, negative 1, and 1. Let's calculate negative 2 times row 2 plus row 1. Of course, that result goes to row 2. Negative 2 times 2 is negative 4. Negative 4 plus 4 equal to 0. Negative 2 times 3 is negative 6. Negative 6 plus 8 gives us 2. Negative 2 times 1 is negative 2. Negative 2 plus negative 4 is negative 6. Negative 2 times 1 is negative 2. Negative 2 plus 4 equal to 2. When we move to row 3, negative 4 plus 4 equal to 0. Negative 5 plus 8 equal to 3. K squared minus 6 plus negative 4 equal to k squared minus 10. And k plus 4 is simply k plus 4 itself. To convert this 2 to 1, we have to multiply row 2 by the reciprocal of 2, that's 1 over 2. To change this 3 to 0, we can add it with negative 3. If we multiply this 2 by negative 3 over 2, it gives us negative 3. Thus, the formula that can change this 3 to 0 is negative 3 over 2 times row 2 plus row 3. Let's copy row 1 elements as they are. Multiplying row 2 elements by 1 over 2 gives us 0, 1, negative 3 and 1. Negative 3 over 2 times 0 is 0. 0 plus 0 equal to 0. Negative 3 over 2 times 2 is negative 3. Negative 3 plus 3 gives us 0. Negative 3 over 2 times negative 6 is 9. 9 plus k square minus 10 gives us k square minus 1. Negative 3 over 2 times 2 gives us negative 3. Negative 3 plus k plus 4 is k plus 1. This is the form which we were aspiring. The elements in these two positions decide whether the system of equation has infinitely many solutions, no solution, or unique solution. The given system of equation has infinitely many solutions only when both of these elements are 0. The first expression, that's k square minus 1 equal to 0, only when k equal to 1 or k equal to negative 1. And k plus 1 is 0, only when k equal to negative 1. Both expressions become 0, only when k equal to negative 1. Therefore, when k equal to negative 1, the given system of equation has infinitely many solutions. If necessary, we can draw a general formula for that infinitely many solution just by substituting negative 1 in place of k and assigning any letter to any of the three variables. If we assign a to x, we can draw this kind of general formula: a for x, 3a plus 1 for y, and minus 5a minus 1 for z. The system has no solution only when k square minus 1 is 0, but k plus 1 is any constant different from 0. When k equal to 1, k square minus 1 is 0, but k plus 1 is 2. Thus, the system has no solution only when k equal to 1. The system has unique solution only when k square minus 1 and k plus 1 are non-zero constants. When the values of k are different from positive 1 and negative 1, both k square minus 1 and k plus 1 are different from 0. Therefore, the system has unique solution only when k different from plus or minus 1. This concludes part 24. I hope you enjoy all the explanations. If you have a real desire to demystify all the enigmas on matrix and determinant, just revisit all the 48 videos I uploaded in both English and Amharic languages. If you do that, with no doubt, you can master your knowledge on the subject matter. Have a nice time. Bye bye.